Today we're learning about isosceles and equilateral triangles. First, we're going to review what an isosceles triangle looks like. An isosceles triangle has two congruent base angles. A triangle or an isosceles triangle also has what we call a vertex angle. And lastly, an isosceles triangle has what we call two legs, and of course, the base of the triangle. Within an isosceles triangle, the legs are congruent. So to go through these vocab words really quick, the congruent side of an isosceles triangle are its legs. Again, notice it says congruent sides, so those two legs are congruent. The third side is called the base. That's this side here. The two congruent legs form the vertex angle, meaning these two legs come up and they intersect at the vertex angle. And the other two angles are called the base angles. And I'm just going to add a little note in here that the base angles are congruent. There's a few theorems that we're going to go through. The first theorem is the isosceles triangle theorem. This states that if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So if we have this side and this side congruent, then we automatically know that the angles across from those congruent sides are also congruent. And I'm just going to draw a little trick in here. Because these two sides are congruent and you see the little tick marks, if you just draw an arrow on the tick mark, that points to this angle, and an arrow on this tick mark points to this angle. So that's how you know which angles are congruent. Also, recall that the legs here and here always come together to form a vertex angle. So the vertex angle is not one of the base angles. The converse of this theorem says that if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So this works backwards. This says that you're starting with congruent angles first, and the sides opposite these angles are congruent. So the isosceles triangle theorem, you're going to start with congruent sides. The converse, you're going to start with congruent angles. For the last theorem, if a line bisects the vertex angle of an isosceles triangle, then the line is also perpendicular to the bisector, is also the perpendicular bisector of the base. This means if you cut through that vertex angle and you bisect perfectly, just like that, we create two congruent angles. That's telling you that we also just created two congruent parts on the base. This is perpendicular, it forms a right angle. If you look at my note sheet on these vocab words, I did add in a few extra notes. So if you need more clarification on that, please check out my note sheet posted on the website. Okay, moving on to the examples. The first example, we need to name two unmarked congruent angles. So we're going to look at this diagram. And I'm going to notice that right here, we have an isosceles triangle. I recognize that we have an isosceles triangle because I see that I have two congruent legs. If I have two congruent legs and I draw an arrow off of these, I know that my base angles must be congruent. So two unmarked congruent angles would be the two angles that I just marked, and I'm going to label them as angle ACB and angle B. So angle ACB is opposite segment AB, and angle B is opposite segment AC. So like I mentioned, angle ACB is congruent to angle B. That would be these angles here. And that is because of the isosceles triangle theorem. For number two says to name two unmarked congruent segments. Here I have another isosceles triangle, different than the first one that I highlighted. I see that I have congruent base angles. So based on the converse of the isosceles triangle theorem, if you have congruent base angles, then the legs across from that are also congruent. But notice that I already have a tick mark here because it's congruent to this one. So we actually have all congruent sides, or all congruent legs on these triangles. Either way, that point doesn't really matter. What matters is that you know segment AD is congruent to AC, and it's because of the converse of the isosceles triangle theorem. So segment AD is opposite angle ACD, and segment AC is opposite angle D. So segment AD is congruent to segment AC. I'm labeling this as the converse because we started with the angles, and remember we made that note when we were going over the vocab words. Next, we're going to use the isosceles triangle theorem to find each measure. So number one says, is segment AB congruent to segment CB? And I did already mark up this diagram a little bit for you. So segment AB is this segment here. And we want to know, is it congruent to segment CB, which is this segment here? So notice that we have two marked congruent base angles. Based on the isosceles triangle theorem, if you have converse of the isosceles triangle theorem, if you have congruent base angles, then the legs are also congruent. And I'm looking at this as a large triangle. So those base angles are the base angles of the entire triangle I just highlighted in purple. So what I said was, yes, segment AB is congruent to segment CB. The converse of the isosceles triangle theorem says that if the base angles are congruent, base angles A and C, then the sides opposite the angles are also congruent. So the main part, or the takeaway from this right here, is that segment AB and segment CB are congruent. Number two says, is angle A congruent to angle DEA? Angle A is this angle here. Angle DEA is this angle here. So if I highlight that triangle in purple, we're looking at the smaller triangle. And the given information shows that the legs are congruent. If the legs are congruent, then so are the base angles. That is by the isosceles triangle theorem. So again, the takeaway here is that angle A is congruent to angle DEA, and my rationale says that the isosceles triangle theorem states that if two legs are congruent, then the angles opposite those sides are congruent. For the next example, we are asked to find the value of y, and y is this angle located here. So this is actually using the third theorem that we went over on the previous page, and I have a note to share with you. It says, if angle M is bisected, then the line bisecting it is also the perpendicular bisector of the base. That's exactly the theorem I shared with you on the previous page. And then this indicates right angles and congruent segments. So if this line here bisects the triangle, it bisects this angle to two congruent angles, but it also bisects the base to two congruent segments. So if I erase my purple highlighter, you can see that I already had a triangle highlighted in the tealish color here. And at this point, you can see that we're looking at a small triangle. We have a 90-degree angle. The 90-degree angle is formed from that bisector. Of course, I drew it in because it is assumed with the perpendicular bisector. So 90 degrees from this angle plus 63 degrees plus angle y is equal to 180 degrees by the triangle angle sum theorem. So if we solve for y, we have 63 plus 90, which is 150 degrees. And if we subtract that from both sides, 63 plus 90, I did 60 plus 90 in my head really quick, that's 153. So oops, back up. All right, so 180 minus 153 is going to be 27 degrees. That is your value of y. And now moving on to equilateral triangle theorems. So equilateral triangles are still a form of isosceles triangles. I'm going to make that as a note. So if equilateral are still considered isosceles triangles, then all previous theorems still apply. So you can think of this idea as a square is considered a rectangle. It's still part of the rectangle family, it just has its own specific name. So same thing with equilateral. Equilateral triangles are still isosceles. They just are a specific form. The first theorem states that if a triangle is equilateral, then the triangle is also equiangular. That means if we have three congruent sides, we have three congruent angles. Three congruent sides leads to three congruent angles. And the converse states that if you have three congruent angles, then you automatically know you have three congruent sides. So it is the opposite, working in the opposite direction. The three congruent angles leads to three congruent, sides. And remember that the interior angles of a triangle sum to 180 degrees. If every angle in a triangle is congruent, 180 divided by 3, because there's 3 equal angles, would give you 60. So without any further information, you can automatically assume that every angle in an equilateral triangle is 60 degrees. Okay, and to go over a couple of examples. The first one, it says find the measure of angle Y. Angle Y is this angle here. So, recall that we have a lot going on here. We have two congruent sides. Two congruent sides means two congruent base angles. If we have two congruent base angles, and we know that the third angle is 60 degrees, I'm sure based on what I just said, you all know that measure of angle Y, but I'm just gonna write out the math to finding that. The angle measures of a triangle sum to 180 degrees. I know that my two base angles are exactly the same, so I'm going to label them with X. If we did 60 degrees plus X, and set this equal to 180, we could solve and we could say that 2x is equal to 120, divide both sides by 2, and x is equal to 60. So while I'm sure you already knew that the measure of angle Y was equal to 60 degrees, what I just wrote out there is the work that goes along with that. Number 2 says to find the measure of segment YZ. Segment YZ is this segment here. Now, based on number 1, if all angles are 60 degrees, then the triangle is an equilateral, and therefore all sides are congruent. So based on part 1, we know that all sides are congruent, and if the previous two sides are 8 inches, then we know that segment YZ is also 8 inches, based on the isosceles and equilateral triangle theorems. And lastly, our example set 5, but the last number, is to use this diagram, and we need to solve for variables x and y. So I'm going to start with the variable x, and the reason why I'm going to start with variable x is that I see that I have two congruent sides. So based on the isosceles triangle theorem, if I have two congruent sides, then I have two congruent base angles. It's the angles across from those sides. So not only are those two angles congruent, but because I see that this one is already 2x and this one is already 2x, I know this angle must also be congruent. So I know that every angle in this figure sums to 60 degrees. So knowing that every angle is equal to 60, I know that every angle is represented with 2x, so 2x must equal 60. and in that case, x is equal to 30. Because we now know that we have an equilateral triangle, because we have 3 equal angles, we also know that every side is equal. So knowing that every side is equal because of what we just found out with the x variable, we know that this segment is congruent to this segment, and therefore I can set those segments equal. So I can do 3 is equal to 4y minus 5. I'm going to solve for y, so I add 5 to both sides. 8 is equal to 4y. I'm going to divide both sides by 4, and y is equal to 2. Okay, that's it for today's notes. Today has 5 different theorems on it, and you can mix and match the 5 theorems to accomplish whatever you need to. Of course, you can only use the equilateral triangle theorems when you actually have an equilateral triangle, but the isosceles can be used with any of these figures. Please let me know if you have any questions.